The heavens bespeak the glory of the Lord, and the vault of heaven reveals his handiwork. In August 1977, the American space probe Voyager 2 left Cape Canaveral on a journey that would eventually take it, several years later, to the vicinity of our solar system's outermost planets. What Voyager discovered once it arrived there fully corroborates ancient knowledge.
Oh my God! For the first time, man is actually seeing Uranus. And it is exactly as the Sumerians had described it 6,000 years ago. Yes, no doubt. Though they had no telescopes, the Sumerians did describe Uranus as Mash Sig, meaning bright greenish.
The Sumerians also explained why Uranus is tilted.
Uranus took an almighty bang early on. A collision with something the size of Earth, traveling at 40,000 miles per hour, could have done it.
What a strange feature. Is it artificial? Was someone there on distant Miranda in the past?
The Sumerians called Uranus planet which is the twin of Neptune, that is. Were they right? Now we can confirm the Sumerian description of Neptune as a blue-green planet. Obviously, the Sumerians must have known.
Is it possible that mankind is only just catching up with ancient knowledge? That the Sumerians were particularly at home with astronomy is evidenced by the fact that they had known, named, and listed all of the planets we know today, including those we ourselves rediscovered only in the past couple of centuries.
Nudimmud, the artful creator. Anu, he of the heavens. Anshar, foremost of the heavens. Kishar, foremost of firm lands. Rakish, the hammered bracelet. Lachmu, their god of war. Ki, the seventh planet. We call it Earth.
Centuries ago, astronomers carefully tracked the motion of the moon and planets in the ancient city of Babylon. Jupiter was a particular favorite because it represented their main god, Marduk. Babylonian astronomers meticulously recorded their observations in cuneiform on clay tablets using simple mathematics. But the recent translation of several tablets shows that the Babylonians did something more. Sometime between 350 and 50 BCE, Babylonian astronomers used sophisticated geometry to track the motion of Jupiter, 14 centuries earlier than when historians had first thought such techniques were developed. To compute Jupiter's position, they focused on its movement along the ecliptic. The ecliptic is the path that the sun appears to trace through the stars. The Babylonians charted Jupiter's daily motion against time. The chart produces a trapezoid, with the area of the trapezoid showing how far along the ecliptic Jupiter had traveled in a given amount of time. Although the tablets show no actual drawings of trapezoids, the calculations demonstrate that the Babylonians were in effect computing the area under a curve to achieve an astronomical result. That feat not only demonstrates the acumen of these early astronomers, but foreshadows the 17th century invention of calculus, the mathematical backbone of modern physics.
an eternal story was written where it all began. We hunted and gathered for thousands of years around the Euphrates and the Tigris. We, humans, came together for the first time and built temples. This was the place that we cultivated the soil, and we grew wheat for the very first time. And we established our first villages beside those fields. We rode our first caravans here. Civilizations merged here, and it was here that cultures flourished. We found our faith here. We built our temples here. We laid the foundations for the sciences here. We developed together here. With countless works of art and diverse cultures, we began to write the saga of civilization here. This is Mesopotamia, the place where the story began and continues to endure.
Going to Mars is not Star Trek. It's not go where no man has gone before, as they say. It's really all about letting our planetary scientists be the pioneers, be the group that scouts the future and looks at resources that we can use on the planet. What are the things they need to know to be able to safely land, live, and return from Mars? The scientific knowledge, the technologies that we need that can make human exploration of Mars happen are within our grasp. In our lifetime, we actually can see humans land and work on Mars. A major step in this direction of planning has been the definition of what we call human exploration zones. This is a region we will land, we will live, we will use resources in many different ways, and we want to go to a variety of scientifically exciting locations. Do it in ways that humans, and only humans, can do. And so our orbital assets are critical to be able to determine and look for those right landing sites. In addition to that, you may not know that they are also relay satellites. These relay satellites are critical to support our landed assets. Our communication will also increase significantly from typically the radio frequencies that we use today to perhaps optical communication. That'll be a critical communication technology that will allow high bandwidth data, voice, but also video, so necessary to support human exploration on the surface of Mars. There's a variety of in situ resource utilization experiments that are being thought about and planned. These are important to understand the area of our landing sites. Power systems and energy systems will be deployed that are very new and unique. Supply of oxygen and carbon in the atmosphere is how we can extract oxygen in the quantities, but also sufficient water. we now know there are regions on Mars for which there may be an abundant source of water. So these observations that we are making are revolutionizing our concepts of how we're going to use the resources to live and work on Mars. So, why are we going to Mars? Well, because as scientists, it's really a step in terms of finding life beyond Earth. You know, exploration is really in our genes. It's a very integral part of what we are all about as humans. But as a human species, if we're going to survive, we need to move off this planet and on to the next object. And Mars indeed is that next object. So Mars gives us a wonderful opportunity to explore scientifically today. But in our future, it is a location where we can go, we can live, work, in addition to return.
The Abbasids were the second dynasty to rule the Islamic world. At that time, the political center of the Islamic world shifted from Syria to Iraq. In 762, a new seat of government was established with the new city of Baghdad. From there, the Abbasids ruled over an empire that stretched from northern Africa to Central Asia. The city of Baghdad, or as it was originally called, Madinat as-Salam, the city of peace, was constructed as a round city with the palace and the main mosque located at the center, with the markets immediately adjacent to these. The circular design of the city was a direct reflection of traditional Persian urban design, most notably of Ctesiphon, the capital of the Sasanian Empire. The first 3 centuries of Abbasid rule are considered the Islamic world's golden age. Baghdad, together with the port of Basra in southern Iraq, developed into the economic center of an international trading empire with contacts in the Far East and Europe. Culture and science flourished at the court of the Abbasid caliphs. Lasting achievements in geography, philosophy, medicine, astronomy, mathematics and engineering were nurtured and acclaimed. The Abbasid period also witnessed a great revival of the arts and crafts. The textile industry was of major importance, producing fabrics of brocade and silk. Ceramic production experienced a virtual rebirth, utilizing new decorative techniques such as luster glazing. An important impetus behind these innovations was the arrival of Chinese wares now finding their way to the Middle East. The adoption of paper technology from China revolutionized Islamic book production. Eventually, Baghdad became too confined for the caliphs. In 836, a new capital was founded. This was Samarra, Suraman Ra'a. He who sees it is delighted. Samarra developed into a mega-urban system, extending nearly 50 kilometers. Samarra testifies to Abbasid grandeur particularly well. Like other Eastern potentates before them, the Muslim caliphs resided in expansive palaces surrounded by extensive gardens, hunting grounds and racetracks. At this time, highly regimented court protocol was observed. In the end, however, a financial crisis forced the caliphs to return to Baghdad. Samarra was abandoned in 892. The Golden Age was over. In the 9th and 10th centuries, new independent Muslim dynasties emerged in North Africa, Syria and Iran. Even Baghdad was conquered in 945. A new era began when the caliphs were replaced by sultans. But the region remained Islamic, and the legacy of Caliph al-Damascus and Baghdad was not lost.
الجلال والجمال والثناء والبهاء في رباك في رباك، الحياة والنجاة والهناء والرجاء في هواك في هواك. هل أراك سالما منعما وغانما مكرما، سالما منعما وغانما مكرما. هل أراك في علاك تبلغ السمات تبلغ السمات. موطني 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 موطني، الشباب لن يكل همه أن يستقل أو يبيد أو يبيد، نستقي من الردى ولن نكون للعالم.
Since the dawn of consciousness, philosophers, poets, musicians, explorers, and scientists have been inspired by the heavens. This laboratory of the open night sky could be studied by anyone yearning to understand its secrets and significance to our daily lives. The birth of Islam in the 7th century, however, invited an even closer investigation of this celestial shroud, producing extraordinary spiritual, practical, and intellectual benefit for mankind. For Islam, astronomers determined the time for prayers and the direction of Mecca from any place on earth. They produced a lunar calendar and determined the dates of Ramadan and Hajj. For society, astronomers determined the length of a year, the seasonal landmarks for the successful cultivation of crops, and they created accurate tools for navigation over land and sea. The progressive power released by astronomy meant that it enjoyed generous patronage and conferred status to anyone associated with it. With this support and breakthroughs in related sciences like trigonometry, astronomy blossomed into one of the most prestigious and practical sciences of this time. This great success story began as medieval Western civilizations sank into the Dark Ages and a period of scientific and cultural degeneration. Valuable manuscripts and ancient wisdom were disappearing fast, neglected, destroyed, or simply forgotten. With the birth of Islam, the true value of this ancient knowledge was recognized. Gathering and consolidating this ancient knowledge was the first step along the road of Islamic astronomical discovery. Visionary patrons like the 9th century Caliph al-Ma'mun sent their men to gather these treasures from the far reaches of the world and bring them to the House of Wisdom in Baghdad. Here, the manuscripts were translated into Arabic, studied, corrected, and substantially expanded upon by Islamic polymaths and specialist scholars. So dynamic was the intellectual effort of the time that even before the ink was dry, new discoveries were being made, new techniques developed, and new instruments invented. Among the first manuscripts to be translated were Eratosthenes' calculations of the circumference of the earth, and Ptolemy's great work known as the Almagest to Arabic scholars. In this book, which formed the basis for cosmology for the next 500 years, Ptolemy described the movements and pathways of a geocentric universe. As Arabic was commonly spoken and written by most Muslims, sharing this newly found knowledge knew no boundaries. Islamic scholars soon distinguished themselves through their empirical, practical, and integrated approach to research. This led to a new era of achievement, in which the blossoming of many related sciences such as geometry, trigonometry, navigation, cartography, instrument making, and even agriculture would redefine astronomy and set it on a new path of progress and innovation. The Caliph al-Ma'mun was astronomy's first great patron and a key architect of this new era. He was the first person to create and build a formal observatory with a library, study, accommodation, and instrumentation workshop. His idea of a large fixed working observatory with dedicated scholars that worked with focus to produce detailed astronomical tables, accurate star charts, calculations of the position of the planets, lunar phases and eclipses, accurate estimates of the diameter, circumference and inclination of the Earth, as well as information for calendars, was truly novel for the time. He built the first observatory in Baghdad, and a second soon followed in Damascus. Other sophisticated Islamic observatories followed later, like the Maraha Observatory, founded by Hulagu Khan in the 13th century in Iran, the Ulugh Beg Observatory in the 15th century in Samarkand, the Malik Shah Observatory of Isfahan, the Tabriz Observatory of Ghazan Khan, and the short-lived Istanbul Observatory, established in the 16th century by Taqi al-Din. A strong focus at the observatories was the development of better and more accurate instruments for astronomy, geodesy, and navigation. These instruments included the sextant and quadrant used to measure the altitude and movement of celestial objects, the universal and Fakhri and spherical astrolabes, 2- and 3-dimensional models of the heavens that help determine the time of day and the position of Mecca from any place on Earth, the navigational compass, the celestial and terrestrial globes, and the armillary sphere, a series of concentric rings that showed how the universe worked. Islamic scholars were the real pioneers of huge observational instruments that dramatically reduced the margin for error. The observatory at Damascus had a 6.1-meter quadrant and a 17-meter sextant. The Maraha Observatory also had many large instruments including quadrants, armillary spheres, and astrolabes. So who were some of the great Islamic minds of this golden age that unlocked heaven's secrets and plotted the celestial paths of moons, comets, planets, and stars? Al-Battani, born in Haran, Turkey, worked in Baghdad. As an astronomer and mathematician, he compiled the Sabian tables, which would influence astronomy for centuries. He predicted new moons and eclipses, calculated the length of the year, and explained the phenomenon of parallax. He also recognized that our solar system moves through space and, as a result, made significant amendments to Ptolemy's observations. Al-Farghani worked in Farghana, Transoxiana, as an astronomer and surgeon. He was the first to explain the mathematical basis of the functioning of the astrolabe and corrected errors in earlier astrolabes. He calculated the distances of planets, the moon, and stars from the Earth. Abdurrahman al-Sufi worked in Isfahan, Iran. In 964, he described the first galaxy known outside our own, the Andromeda Galaxy. He wrote extensively on the astrolabe and star positions, their sizes and colors. Ibn Yunus worked in Fustat, Cairo, Egypt, and compiled the Hikmat tablets. Using a large astrolabe nearly 1.4 meters in diameter, he recorded over 10,000 entries for the sun's position over a 30-year period. Born in Iran, a hotspot for early astronomers, Al-Biruni was a classic polymath with expertise in mathematics, astronomy, geography, pharmacology, physics, and geosciences. Amongst his many discoveries, he observed that the Earth revolves around its own axis, calculated the Earth's circumference, and accurately determined the direction of Mecca from any point on the globe. Al-Zarqali worked in Toledo, Spain, and compiled the famous Toledan tables. He developed a sophisticated astrolabe called the Safiha that could be used at any location. Jabir ibn Aflah worked in Seville, Spain, as an astronomer and mathematician. He was highly skilled in spherical trigonometry and designed a portable celestial sphere, today known as a torquitum, for measuring celestial coordinates. Ibn Rushd worked as a philosopher, physician, judge, and astronomer in Córdoba, Spain. Not only was he one of the most famous Muslim medical doctors, but he also discovered sunspots. Ibn al-Shatir al-Muqit worked in Damascus, Syria, as a timekeeper and astronomer at the Umayyad Mosque. He made many corrections to Ptolemy's calculations on the movement of the moon. These astronomers were some of the greatest minds of the time, and their models, treatises, catalogues, and inventions laid the foundations for the giants of the European Renaissance. Nicholas Copernicus frequently referred to the works of Al-Battani and Al-Zarqali in his famous book De Revolutionibus. Tycho Brahe rediscovered the third equality of the moon's motion 600 years after Al-Bushjani had documented the same observation. Johannes Kepler utilized the works of many Islamic astronomers in the development of his laws of planetary motion. And Galileo Galilei and Isaac Newton's proposals of an early theory of gravity followed on from the work of Al-Biruni and later Al-Haytham. Today, the rich legacy of these Islamic greats lives on in the 13 features of the moon, named after Arabic astronomers, in the 165 stars with Arabic names, and in the many astronomical terms like zenith, azimuth, apogee, and qibla, all derived from Arabic words. As we reach deeper into the mysteries of the universe, we owe much to these early pioneers of astronomy, who, in their fearless quest for knowledge, laid the foundations for modern-day astronomy and space science.